Dear learners, greetings from IIT Guwahati. We are now in the MOOCs course Applied Thermodynamics, that is, and we are in the module 4, and this title of this module is Gas Turbine Engines. So, under these headings we have covered the first lecture, that is gas turbine engines, basic components, thermal circuit arrangements. Today we are going to start a new topic, that is gas turbine performance cycle. So, it has two parts. So, we will cover the first part today, and in the next lecture we will cover its second part. So, in this particular lecture, that is gas turbine performance cycle part 1, we are going to discuss about a practical gas turbine cycle, how it is supposed to operate. Second is ideal gas turbine cycle, because to have a practical gas turbine cycle we must have a theoretical estimates. So, here we will talk about ideal gas turbine cycle, and in fact ideal gas turbine cycle is nothing but the Brayton cycle. This is similar to the concept that when you deal with IC engines, Otto cycles are the ideal cycle for, or air standard cycle for SI engines, and diesel cycle is ideal air standard cycle for diesel engines. And in similar sense, the gas turbine cycle has air standard cycle which is known as Brayton cycle. And for this Brayton cycle we are going to do the thermodynamic analysis. By doing this thermodynamic analysis we are going to calculate the thermal efficiency. Apart from that, important aspect of a gas turbine cycle, because we want to think about how much work output or work ratio you are going to get. So, for that also we are going to find out mathematically what is the specific work output. Now, apart from this ideal cycle, there is some limitations, and for which we require the incorporation of an heat exchanger. So, such a cycle is known as heat exchange cycles. So, in the gas turbine cycle performance, basically there are two variants which works on the Brayton cycle principle, or which work on the Brayton cycle. The first variant is the simple gas turbine cycle, and second one is heat exchange cycle. Now, in today's lecture we will summarize both these cycles. As I mentioned earlier, or in the last class, the most basic gas turbine unit has the two major components, that is compressor and turbine. They are coupled with a shaft, and apart from that we have a combustion chamber where fuel is added, and in our analysis we will say that this fuel is equivalent to heat addition. And finally, that means air comes from the atmosphere enters to the compressor, and finally exhaust gas leaves at the state 4 at the end of the turbine. And by virtue of the expansion process in the turbine we get net shaft work output, and typically we use a constant pressure combustion mode in this cycle. So, this was the summary which we got in our last class, and there the another important aspect is that typically we use rotary compressors driven by the rotary turbines. They are, I mean they are, and they come under the category of turbo machines. And the thermodynamic circuit or thermodynamic cycle is represented in the TS diagram, process 1, 2, 3, 4, and if you look at this particular process 1, 2s, 3 and 4s there, and that is your ideal cycle, and 1, 2, 3, 4 is your actual practical cycle. And here the practical cycle that involves component efficiency for the compressor and turbine, and this part we will going to debate in the subsequent lectures. So, in your first thing we will consider the ideal cycle. that is 1, 2s, 3 and 4s. Another aspect of this is that okay, and as I mentioned earlier, the compressor is either a centrifugal, I mean first thing is that they are rotary in nature, and this under this rotary category we can have a centrifugal or axial flow type compressor, and the process is typically irreversible but approximately adiabatic. And the expansion process is in the turbine, and that is also irreversible but adiabatic. But our analysis, first analysis, when you deal with the ideal cycle, we will talk about the situation where the process is not a reversible one, that is 1, 2s, 3 and 4s. Now, with this summary, we are going to discuss about a ideal gas turbine cycle and the typical processes that goes as process 1 2, that is irreversible adiabatic compression, process 2 3 constant pressure heat supply, process 3 4 irreversible adiabatic expansion, process 1 2s here. So, here the actual cycle 1 2 3 4 completes, and again cycle starts from again 1. But to give a theoretical estimates, we assume that if the process would have been an isentropic one, then we make an assumption it is an ideal isentropic compressions. So, the word is redundant, adiabatic is redundant here. So, process 1 2 is known as an ideal isentropic compression, and process 3 to 4s is ideal isentropic expansion. Now, let us see that why this ideal cycle is very important, because it gives a theoretical estimates. And in the beginning I have emphasized the fact that when you use these gas turbine engines, they are used for two broad groups. One is considered as the shaft power cycle, other is considered as aircraft propulsion cycle. Now, when you talk about shaft power cycle, here the power output is given as a emphasis. Your main concern is that we are going to get power work as a power output, whereas in the aircraft propulsion system, where thrust is given a prime importance, and that gives forward speed. And this aircraft propulsion cycle is depends on altitude, because and forward speed and altitude is more dependent, because higher and higher altitude you go, speed will become more and more, because density comes down when you go with altitude. So, our main concern we will try to see in both the aspects. So, in the first part, gas turbine performance cycle, part 1 and part 2 we will talk about shaft power cycle, and the second part, that is aircraft propulsion system, that is we have 2 lectures on this. So, here that is what we are going to discuss, where we can say the thrust is a main criteria. But currently let us concentrate on shaft power cycle, where work output and thermal efficiency are major concern. Now, when you deal with the ideal gas turbine cycle, assumptions are made, and some of the important assumptions are compression and expansion processes are irreversible adiabatic, or they are considered as an isentropic. Changes in the kinetic energy of working fluid between inlet and outlet is negligible. This is one of the important we assume for the shaft power cycle, but this assumption is not true when you deal with aircraft cycle, because the kinetic energy between inlet and outlet of the components are significant. So, the emphasis is given in a different aspect and in different context in those situations. The third important aspect is that there is no pressure losses in the inlet ducting, combustion chamber, heat exchangers, intercoolers, exhaust ducting and connecting components. Apart from this, the working fluid is same composition throughout, and it is a perfect gas with constant specific heat. Mass flow rate of the gas is constant. The heat transfer in the heat exchanger, mainly countered flow type, is complete, so that temperature rise in the cold side is maximum and exactly equal to the temperature drop in the hot side. So, in the ideal gas turbine cycles, we are going to see two variants. In first variant, there is no heat exchanger, and in the second variant, there is a heat exchanger. Why we think about a heat exchanger? Because when you take a first variant, that is exhaust from the turbine, this particular exhaust situation that is at thermodynamic states at 4, there the gases are at very high temperatures. So, in order to tap those heat, we try to use an heat exchanger that takes the heat from the exhaust and preheats the compressed air. So, this is the main motive that we are going to increase the efficiency of the cycle by incorporating a heat exchangers. So, these two things are known as ideal gas turbine cycle, one with simple cycle, other is with heat exchange cycle. Now, let us see the thermodynamic analysis of the first case, which is a simple gas turbine cycle. So, just to give the explanation, that in the compressor the air is drawn at state 1, it is compressed to and its final state through these compressions the temperature and pressure also goes up. So, it is now in state 2. Now, it goes to a combustion chamber where fuel is added, and in our terminology when fuel is added, which is equivalent to a heat. So, that is basically we are adding heat to the air in our simple analysis of Brayton cycle. And finally, the heated air comes out from this heat from this combustion chamber, which is at state 3, and when it expands in the turbine. When it expands in the turbine, the state goes from 3 to 4, and throughout the process the power output is developed, and out of this power output it is partly used for to drive the compressor, and rest of the rest of the work output we go in the form of work or finally in the form of electricity. Now, this particular process can be represented in the thermodynamically in the pressure volume diagram and temperature entropy diagram. So, what you see is that when the cycle goes from state 1 to 2, it is an compression process. So, it is a isentropic process. Process 2 3 is considered as heat addition process, 3 to 4 is process is expansion in the turbine, and 4 to 1 is the exhaust process. So, here it is written as a cyclic because more or less the point 1 coincides with the point 1, although the cycle is open in nature, but the way we represent in this is a resembles the closed cycle also. Now, similarly, in the temperature entropy diagram, we have two constant pressure lines, that is P1 is equal to P4 and P2 is equal to P3. So, the cycle can be represented similarly 1 2 3 4 and then 4 to 1. Just to give here also I will represent the direction of this thermodynamic cycle. Okay, 1 2 3 4, and this is nothing but the your Brayton cycle. So, you start the thermodynamic analysis with our understanding from the steady flow energy equations, which is Q is equal to H2 minus H1. That means, when there is a change of state, when the system goes from state 1 to state 2, the first law equations can be used for an open flow systems, and here we say that there is no change in the potential energy. So, it is only change in the kinetic energy. So, change in the kinetic energy and change in the enthalpy. This change in enthalpy takes care about the internal energy change as well as the flow work, and the Q is your heat transfer, W is the work transfer. Now, this particular equation we are going to use for our gas turbine cycle, which is ideal in nature. But before you do that, we define some important parameters, that is pressure ratio, which is R is equal to P2 by P1, and temperature ratio, which is T is equal to T3 by T1, and this T3 by T1 is nothing but the maximum temperature to minimum temperatures. So, from this in the combustion chamber, the heat addition process can be represented as a Q23, that is H3 minus H3 minus H2, and since it is air is used as an ideal gas, so it can be represented as a Cp times T3 minus T2. Similarly, compression process, so it is a work consuming device, that is what it is a negative sign, negative of H2 minus H1, and this becomes minus T minus Cp T2 by T1. And apart from that, the compression process is isentropic. So, the relation between T2 pressure and temperature relations can be represented in this manner. And this T2 by T1 now finally comes as a pressure ratio, that is R to the power gamma minus 1 by gamma. And moving to the turbine, this is similar to compressor analysis, but with a fact the turbine is a power producing device. So, it is there is no negative sign here. So, it is the S3 minus H2, and finally, temperature T3 by T4 ratios can be also represented as R to the power gamma minus 1 by gamma. And by definition, we can define the cycle efficiency eta is equal to W net by Q in. W net is nothing but difference between turbine work and compressor work, and when you do it and simplify, and finally, the cycle efficiency for an ideal Brayton cycle is written as 1 minus 1 by R whole to the power gamma minus 1 by gamma. So, the cycle efficiency is written in this fashion. Now, from this equation one can find out that efficiency is a function of two parameters. One is the pressure ratio, other is the nature of working fluid. By nature of working fluid, I mean this specific heat ratio gamma. That means efficiency depends on R and gamma, and of course, it increases with the increase in the pressure ratio. What we can see here, that one can plot for various pressure ratios, efficiencies can be plotted. One for gamma is equal to 1 to the power 1.4 and gamma is equal to 1.66, that is for monoatomic gas. So, that means if you take a value of helium if you use instead of air, if you use helium, its cycle efficiency will go up. Any value gamma comes down below 1.4, their efficiency will will reduce. So, that is the reason that in Brayton cycle does not recommend any gas other than air. But apart from that, we have seen that if you have gamma is higher, the efficiency also goes out. But one interesting thing is that if you take a first thing is that there are many limitations when you deal with the helium, because if you first thing is that helium is a lighter gas and it requires large volume of helium. I mean means you require large volume of helium to run the cycle, and what will happen is that what one particular point or I mean when you deal with the compression pressure ratio, at one particular point, although it increases in the beginning at lower compression pressure ratio it increases, but at higher compression pressure ratio its efficiency falls. When you cycle efficiency falls, of course, and at side by side specific watt output when you calculated kilowatt second per meter cube, then that also falls with the pressure ratio. But at some point of time air takes over, because air is continuously higher. That means a realistic curve, when you use air at a wide range of pressure ratio, it gives a better advantage, it gives a theoretical advantage than the helium. So, because of this reason, the air is the only choice as the working fluid for an gas turbine cycle. And there are other uncertainties that is involved, that we can think of variation of Cp and gamma with temperature. Air leads to almost identical efficiency when you think about helium and air. So, that means when you take the variation of Cp and gamma at higher temperature, the helium and air will have similar identical efficiency. So, over a large domain of pressure ratio, air is the best choice. Moving further, apart from the efficiency, another important aspect of a gas turbine engine is the work output, and here we will analyze a very important factor, specific work output. So, if you look at this cycle in the PB and TS diagram, the cycles are represented as 1, 2, 3, 4, and the directions of the arrows are given in this fashion. Okay. So, here P2 is equal to P3, and that is pressure is constant, and P1 is equal to P4. And here this particular analysis we are mainly will focus on the calculation of specific work output. One ideal way of looking at the work output is the difference between the turbine work and compression work. So, here it is written the specific work means per kg of air, the work output can be represented as W is equal to Cp times T3 minus T4 minus Cp times T2 minus T1. But the other important aspect that we want to use it in a non-dimensional form. So, a non-dimensional expression would be W by Cp times T1. So, basically you take a common Cp times T1 and represent the specific work in this manner. So, it is a non-dimensional form of representation. So, this is a dimensional form of representation. So, this is dimensional form, and this representation is non-dimensional. So, and when you do this, you have to do some mathematical jugglery. So, some simplify the way we can simplify it, and side by side we have to use this conditions that for an isentropic process, what is the ratio of T2 by T1 and what is the ratio of T3 by T1 as a function of pressure ratio. So, this is known to us for an isentropic process. So, ultimately we can get a non-dimensional form of work which is represented as W by Cp times T1 as a function of two important parameters, which is R, that is pressure ratio, and T is nothing but the temperature ratio. So, here the most important things that W by Cp times T1 is function of temperature ratio as well as the pressure ratio. And an interesting thing that for the fact that we can find out from this equation that W is equal to 0 at two locations. When we put R is equal to 1, W is equal to 0. When R is equal to T to the power gamma by gamma minus 1, when you put, W is also is equal to 0. That means, specific work output is 0 at two locations. So, let us see what is this physical significance. Now, to do that, we recall our temperature entropy diagram and try to see the actual cycle, that is, had the cycle been process been represented. So, this is 1, 2, 3, 4. So, this is the actual cycle we have been studying and analyzing. Now, let us see that when W is equal to 0 at two locations, that is when R is equal to 1. So, when R is equal to 1, nothing but that means P2 is equal to P1. So, that means the cycle is if you can see this dotted line, that the expansion in the process in the turbine as well as the compressor, they are very close to each other. So, obviously, there will be no work output. So, this becomes a unrealistic situation, that means why we should go for R is equal to 1. So, there is no meaning as far as the practical utility is concerned. But the very fact that when you put R is equal to T3 by when the R value is this, again the W value goes to 0. So, this represents a situation that we should not operate the R value, the pressure ratio at this number, which means it is close to the other extreme. That means, process goes in this dotted line, instead of 2 it will be like 1, then you will have land in the after compression you will have this 3, 2 to 3 and 3 to 4. And in this case, ideally if you look at both the lines are coinciding each other, that means compressor and turbine work are equal. So, this has also no meaning. So, then what is the better choice? So, that means So, between these two values, that is 1 and this, there should be a optimum pressure ratio. So, this what the mathematical analysis or treatment tells to us. So, for any given value of T, the optimum pressure ratio can be found out for maximum specific work output by differentiating the work equation to D0. And this optimum pressure, and when you do this, we will find out optimum pressure ratio and maximum power output can be obtained. And we will find that then we will see that the specific work output will be maximum when pressure ratios are such that the compressor and turbine outlet temperatures are equal. So, this will tell us that when compressor outlet and turbine outlet temperatures are equal, then work output is maximum. Now, by doing this, so here another plot we can represent that is W by Cp times T1 for the way we have calculated that this W by Cp times T1 is a function of pressure ratio as well as temperature ratio. So, this plot are given for different values of T, that is T is equal to 2, T is equal to 3, T is equal to 4 and T is equal to 5, and some realistic number has been given here. So, let us recall that we were going to find out the condition at which maximum work output can be obtained. So, first thing from our previous analysis, we can see that we have pressure ratio R, temperature ratio T and isentropic relations between T2 and T1 and T2 by T1 and T3 by T4 as a function of pressure ratio. And also we have this non-dimensional form of specific work. So, to have maximum work, we have to differentiate this particular W by Cp times T1 as a function with respect to this particular parameter, that is R to the power gamma by minus 1 by gamma. So, when you differentiate with respect to this, then we will find a conditions of optimum value of pressure ratio, relations between the temperature ratio and optimum value of pressure ratio, and for which we can say T is equal to R optimum to the power twice time gamma minus 1 by gamma. And when you put these particular things, then we will note that this is nothing but situation at which T2 is equal to T4. That means, when you say this, when you recall this particular cycle, that is 1, 2, 3 and 4, we will find that when the state 2 and state 4, this work are equal, I mean the temperature, that is T2 and this temperature at the exit of the turbine is T4, and when both are equal, that conditions will have optimum pressure ratio. But that again it is a very hypothetical situation, we can due to variety of reasons, drop in pressures or losses, pressure losses, we will not land up in that manner. So, it is operated, that means T4 is always higher than T2. So, we will come back to that conclusion later, but here when you put this R optimum conditions, we can find out another expression what is the conditions for maximum work output. That means, W by Cp times T1 maximum situation will be T bracket 1 minus 1 by square root of T minus bracket square root of T minus 1. So, here you can see the maximum work output is only a function of temperature ratio, and subsequently for efficiency at this maximum work conditions would be 1 minus square root of T1 by T3. So, this is another important consequence, that efficiency conditions at the maximum power output. So, this particular study gives some important inferences, that is at two values of pressure ratio, the specific work output is 0, the optimum value of pressure ratio, the specific work output is maximum, and it refers to a equal temperature at the outlet of compressor and turbine. For all values of pressure ratio between 1 and R optimum, T4 is always greater than T2. Hence, there is a necessity to include a heat exchanger to reduce the heat transfer from the external source and increase the efficiency. So, the simple analysis says that simple Brayton cycle analysis tells us that the condition of optimum power is a situation where compressor exit temperature and turbine exit temperature are equal, that is T2 is equal to T4. So, these 2 points must coincide for optimum work output, but that normally does not happen. So, we say T4 is always greater than T2. Because of this reason, the new cycle comes into picture, that means what we other time we would say that is a other variant of cycle, the simple cycle, that is by inclusion of a heat exchanger. So, what the heat exchanger does then, when at the exit of the turbine, it is the heat from the exit of the turbine from the exhaust is tapped by preheating the compressed air that comes out from the compressor at state 2. So, with the process from 4 we have that is that another process goes from 4 to 6, the other process goes from 2 to 5. So, in this process the changes that happens in the TS diagram goes that. So, you have 1, 2 is the compression process, then 2 to 5 is a heat exchange process, then 5 to 3 that is a heat addition process. So, heat addition does in 2 parts, one is preheating part, other is the through the fuel combustion chamber, and then of course, they are in a different pressure line, but ideally we are maintaining at same pressure for our cycle analysis. Then 3 to 4 is the expansion of the turbine, then 4 to 6 is the heat rejection from the turbine in the heat exchanger, and finally, from 6 to 1 it goes from the to the exhaust. So, this is how the cycle operates in a heat exchange. So, we call this as a heat exchange cycle. So, the air standard cycle is now referred as heat exchange cycles, with the main intention to preheat the air inlet to the combustion chamber by tapping heat from the exhaust of the turbine. So, here hence it is the appropriate location is between the outlets of turbine and compressors, and in ideal scenario T5 is equal to T4. So, T5 is equal to T4 with a heat exchange cycle, that is compressed gases can be heated to a maximum limit to the outlet of turbine temperatures. That means, from 2 to 3 we cannot go because it is limited, the heat exchanger has a limiting situation that when T5 is equal to T4, and that means that much heat we can tap. So, now we will go back to this thermodynamic analysis, that is 1, 2, 5, 3, 4, 6, then 1. And here the one thing that we want to emphasize is the fact that when you calculate the net work, it is remains same. That means, because there is no net work remains at which is the difference between the turbine work and compressor work. Now, here we are comparing in 2 aspects, one is the ideal cycle, other is heat exchange cycle. When you ideal cycle, this is nothing but a simple Brayton cycle. So, we check net work output, and also we get this efficiency as a function of pressure ratio. Now, if you recall our analysis with respect to heat exchange cycle, we can find out that the net work output does not change for the heat exchange cycle, and that is quite obvious because there is no extra components that in which work output is derived. But what interesting fact is that heat transfer process, and in the process what we did is that we reduced the value of Q in. So, that means instead of T3 minus T2 which was supposed to be given by this combustion chamber, now it is becomes T3 minus T5. So, that means this particular part was, that means when it goes from actual process, when it goes from 2 to 3, and the first part, that is from 2 to 5, we are getting it from the exhaust of the exhaust gas from the turbine. So, that particular component is gets reduced in by heat transfer process. And finally, when you calculate the cycle efficiency, it is now represented by two terms, that is the cycle efficiency is now function of R and T, whereas in a simple cycle the cycle efficiency is a function of only a pressure ratio. So, these two things are different with respect to heat exchange cycle. Now, let us see when you plot them, actually when you plot them. So, here the plot goes in this manner, that when you plot efficiency versus pressure ratio by considering for an ideal simple Brayton cycle, efficiency is equal to 1 minus 1 by r to the power gamma minus 1 by gamma. We see this is the dotted line. So, this is the typical nature of the plot. Now, on this we are superimposing the another efficiency term for heat exchange cycle. So, when you put the efficiency of heat exchange cycle, so it is a function of 1 r as well as t, that is 1 minus r to the power gamma minus 1 by gamma divided by t. So, for different values of t, we get the curves like this. So, that is this curve shows for t is equal to 5, then 4, then 3 and then 2. But the interesting fact is that at some point when you keep on, when you see here that for an simple cycle, with increase in the pressure ratio, the efficiency goes off. But when we, for a heat exchange cycle, with increase in the pressure ratio at a given temperature ratio, the efficiency fall. This is the quite interesting factor. So, these are the two contradicting factors, but one point of time somewhere at some locations they intersect each other, and in fact this is the optimum locations that we have to use. That means we have to use this particular temperature, but for that we have this is the optimum pressure. So, this is how your understanding should go. So, whatever I explained, if you can make some inferences, we can write like this, that with an addition of heat exchanger, there is no change in the specific work output in a heat exchange cycle as compared to Brayton cycle. So, efficiency of heat exchange cycle is always higher when the temperature ratio increases. For a given value of temperature ratio, the cycle efficiency increases with decrease in the pressure ratio. For a given value of temperature ratio, the cycle efficiency decreases with increase in the pressure ratio, or we can say in a reverse way. But in contrast, the cycle efficiency increases with increase in the pressure ratio for an ideal Brayton cycle. And another point is that the upper limit of constant T curve starts with r is equal to 1. So, now in this if you look at this particular plot, when you put r is equal to 1, it gives a situation that it is nothing but when you put r is equal to 1, efficiency becomes 1 minus but at r is equal to 1, your efficiency becomes 1 by T, and that is nothing but 1 minus T1 by T3. So, this is nothing but your Carnot efficiency. So, this says that as expected that limiting case the cycle efficiency is nothing but the Carnot efficiency. So, it is the limiting case for the requirement of complete external heat reception and rejection at upper and lower cycle temperatures. The lower limit of the constant T curve stops at the optimum pressure ratio is reached. So, these are the locations where this constant T curve and simple cycle intersect. So, and this particular intersecting points we call as a optimum pressure ratio, and the optimum pressure ratio refers to a situation where the turbine outlet temperature and compressor outlet temperatures are equal. For higher values of pressure ratio, that is beyond optimum value, the heat exchanger would cool the air leaving the compressor and cycle efficiency is reduced. That means, Beyond these locations, normally these curves are not extended, because it will have a different interpretation that heat exchanger will not play its role. That means, the air leaving the compressor would be cooled instead of getting heated. So, finally, in order to obtain appreciable improvement in the efficiency by heat exchange, there are two possible situations. One is operating pressure ratio is lesser than the optimum value is used for maximum specific work output. Other option is that always it is not necessary that you to use higher cycle pressures. So, one way is that if you one way to increase the efficiency is that either you go for higher temperature ratio or you go for higher pressure ratio. But what will happen is that higher pressure ratio will have a lot of other complications, because you require many kind of rotary devices in the through the compression mode. So, the better option would be to go for a heat exchange cycle with higher temperature ratio. Through this, obviously we will land up in getting higher pressure ratio at some location. For example, if you take a T is equal to 4, we will land up a pressure ratio which is optimum at maybe at R is equal to 11. But for that means we can achieve this pressure ratio in a heat exchange cycle with T is equal to 4, for which we need not have a very big compressors which can give you the pressure ratio of similar number. So, eventually it is the fact that the use of heat exchange cycle is a very significant aspect in a inclusion of heat exchange or heat exchange cycle is a very significant aspect for gas turbine engines. And finally, we will say that if you want to use operate a higher pressure ratio lesser than optimum value, then we require certain modifications. So, what modification we will do, we will see in the next class. Okay. So, from the basic variant of simple gas turbine cycle and a heat exchange cycle, we will have few modifications that can be used for its practical utility to account for the fact that we have to get appreciable improvement in the heat efficiency by heat exchange. Okay. So, after this we are now going to solve some numerical problems. So, in these numerical problems we have a basic aspect that we have covered here is the simple Brayton cycle. So, for a simple Brayton cycle, first thing when you look at the Brayton cycle, first thing that we are going to draw is the temperature entropy diagram for a Brayton cycle, and we have to represent the cycle diagram 1, 2, 3, 4. 1, 2 compression, 2, 3 heat addition, 3, 4 turbine and 4 to exhaust. So, now let us see the question that in a Brayton cycle air is drawn at atmospheric pressure 1 bar and 30 degree centigrade into the compressor. So, state 1 is known. The maximum pressure and temperature of the cycle is limited to 7 bar and 800 degree centigrade. So, that means P2 and P3 are P2 the maximum pressure, that is at state 3 the pressure at temperature is given. So, to start let us recall the data that we have P1 as 1 bar, T1 as 30 degree centigrade. So, this turns out to be 303 Kelvin. Then P3 that is 7 bar and T3 that is 800 degree centigrade. This turns out to be 1073 Kelvin, and heat addition here, heat supply is Q23. Sorry, it is total heat because mass flow rate is involved. So, it is Q23 is 90 megawatt or 90 megajoule per second. So, you have to going to find out thermal efficiency, work ratio, power output, exergy. So, to start with, let us recall the first expression, efficiency of a simple Brayton cycle, that is 1 minus 1 by r to the power gamma minus 1 by gamma. So, here r is given, so we can find out r, which is P3 by P1 7, gamma we can take as air as 1.4. Of course, we require Cp, that is 1.005 kilojoule per kg Kelvin. So, from this equation, if when you put these numbers, so efficiency value becomes 0.42 when you put r is equal to 7 and gamma is equal to 1.4. Second problem is work ratio. To find work ratio, we say that is work ratio is nothing but turbine work minus compressor work divided by turbine work. So, turbine work we can find out Cp times T2 minus T3 minus T4, and compressor work will be Cp times T2 minus T1. So, of course, we know the relations, that is T2 by T1 is equal to r to the power gamma minus 1 by gamma, T3 by T4 is equal to r to the power gamma minus 1 by gamma. So, from these equations we also know r, we know T1, we know T3. So, we can find out from this all this number, we can find out two important numbers, that is T2 is equal to 527.6 Kelvin and T4 would be 616.2 Kelvin. So, you can see that T4 is greater than T2. So, of course, his exchanger is more effective here. So, that is a separate part, but when you put this, when you have all these numbers, we can find out turbine work, we can find out compressor work. So, Wt is nothing but you can find out as 459 kilojoule per kg. W compressor work would be 225.7 kilojoule per kg. So, by putting this, we can find out the work ratio as 0.5. Okay. So, we got this work ratio. Third point is power output. So, power output we can find out, that is from efficiency, we know efficiency, that is W net by Q in is 0.42. So, W net can be find out 0.42 into 90, this becomes 37.8 kilojoule per second, sorry megajoule. So, here Q in 90, so it is this. And last part is exergy. So, exergy, here you can see that finding exergy in the exhaust gas leaving from a gas turbine unit. So, here the exergy that we get, it is a exergy in the form of heat. So, we can call this as a X heat, that can be written as integration of, that means you have to see what is ambient temperature, that is T0, and what is your final temperature, that is T4, that is 1 minus T0 by T delta Q. So, this is the expression for exergy which comes out of heat. Now, if you integrate this, we get a simple expression, that is Q can be written as m times Cpt, Cp delta T. So, we can write down this particular expression after integration will be m dot Cp T4 minus T0. T4 is the turbine exit temperature and T0 is your ambient temperatures. So, these conditions can be taken as 30 degree centigrades. This is first part, and second part will be m dot Cp T naught ln. When you second part, when you integrate, we will have ln T4 by T0. Okay. So, all these numbers are known except this m dot, and this m dot can be calculated as from the fact that we know Q in m dot Cp into T3 minus T2. Okay. So, T3 is known, T2 also we find out. So, and Q in also known as 90. So, from this we can find out m dot as 164.2 kg per second. Now, when you put all these things here, m dot Cp T4 T0, all the parameter we can is put, we can find out x heat as 16.5 megawatt or megajoule per second. So, it means that this exhaust heat has a tremendous value of energy, that is about 16.5, which could have been trapped, and because of this reason we say that effectiveness of heat engine is a heat exchanger is realized. Now, we will go to the next problem. Next problem is also similar nature, but here we will more try to concentrate on some important aspect, that is about maximum work done and how you are going to compare with a Carnot efficiency. So, it's same realistic number and the previous example where the operating temperature limits are 30 degree centigrades and 800 degree centigrades. We have to find out for a Brayton cycle the maximum specific work done and optimum pressure ratio, cycle efficiency and ratio of cycle efficiency to the Carnot efficiency. So, here the problem is simple, with the fact we have to refer a situation for maximum specific work output condition. So, W by Cpt max is possible when we can write them as in a function of, that is only a function of temperature ratio, 1 minus 1 by square root of T minus square root of T minus 1, where T is nothing but T3 by T1, and T3 by T1 means 800 plus 273 divided by 30 plus 273. So, this number is 3.54. So, from this we can find out W by Cpt maximum is 0.77. So, if you put Cp and T as its absolute value, so T may be T1. So, T1 may be 30 degree centigrade, Cp would be 1.005 kilojoule per kg Kelvin per air. So, this will give you W max is 234.5 kilojoule per kg. So, you can get this much of maximum work from these situations. And second thing, and or I will say instead of maximum work I will correct it as optimum, because this is as optimum condition. So, optimum is a right word. Okay. And for this situation we can say optimum pressure ratio, this first part. Second part would be R optimum. R optimum and temperature ratio relations could be R optimum to the power gamma minus 1 by gamma is equal to square root of T. So, from this we can find out R optimum as, because you know T as R optimum as 9.1. So, optimum pressure ratio is 9.1. Third is, for this optimum pressure ratio, what is the cycle efficiency? So, Brayton cycle efficiency at optimum pressure ratio is, that is 1 minus square root of T1 by T3. So, T1 and T3 are known. So, this number would be 0.47. Now, last part we have asked that we have to find out Carnot efficiency. So, recall that if you take the Carnot efficiency between these two temperature limits, so it will be 1 minus T1 by T3, and this number is 0.72. And finally, it's the ratio. So, that means eta B by eta C would be 0.47 by 0.72, 0.652. The ratio of a Brayton cycle efficiency at optimum power is about 65% of the Carnot efficiency, and this is how the air standard cycle, this is how it says that it is the optimum air standard efficiency of a Brayton cycle when you compare with the Carnot efficiency. So, with this let us conclude for today. Thank you for your attention.